All right. Yeah, so value iteration was nothing more than applying the Bellman backup operator over and over and over. In the original algorithm that we talked about, you apply it in a very systematic, deterministic way. You just apply it to all the states, and then you do an update, then you apply it to all the states again. But it's a very simple operator. It's basically doing a one-step look ahead, and then backing up the value. So what we said is that if you run value iteration for an infinite number of iterations, it will converge to the optimal value function. And that's good. It tells you that the algorithm's sort of convergent and well-defined in a sense. It doesn't tell us when to stop running because we can't run till infinity. So we'll talk about that. And so today we're going to partly talk about why does it converge, why is the algorithm correct, and then when should we stop. And if we have time, we'll move on to one other type of algorithm called policy iteration, which will be useful because that's the basis for some other types of reinforcement learning algorithms. Basically, all reinforcement learning algorithms usually will derive from one of these basic algorithms that we're going to be talking about. So recap, the Bellman backup operator, we're going to think of it as an operator on vectors. So this value function was a vector with a number of elements equal to the number of states. And the Bellman backup operator takes a vector and returns a value vector. Right? And we're interested in what properties of that operator allow it to converge. Like why does it converge? And there were two properties. The first property that we talked about was a fixed point property, which basically says that if you apply the Bellman backup operator to the optimal value function, it returns the optimal value function. Right? It's kind of what seems like you would kind of need that for this thing to converge to the optimal value function. So it turns out that, and since there's a unique value, optimal value function, there's going to be a unique fixed point. So the other thing we need is we need to be able to show that when we're not in an optimal value function, somehow we make progress towards the optimal value function, right? We have some random vector here of values, and we want to show if we apply the Bellman backup, it will make some progress towards the optimal value function. And that property turns out to be something we call the contraction property. And what this is you first need to have a notion of distance. Like when I say it gets closer to the optimal value function, what do we mean? Well, that's the max norm, and the max norm just returns the maximum absolute value. Okay, and so what I want to think about this first, so that we make sure we understand what the max norm is. So v minus v prime, right? Those are two different value functions. Intuitively, what does the max norm return when we have v minus v prime? So what is it returning?
Vector of distances between each of the dimensions.
The norm will just return, so v minus v prime is the vector of differences. The norm will return a single number.
The maximum change of value of it.
Right. So v and v prime differ at one state. There's a maximum difference if you look at all the states between v and v prime, right? And the max norm returns what that maximum difference is. So the two states that have values that are furthest apart from each other is what the max norm will return. Okay? And what we're going to show is that the Bellman backup basically makes that smaller and smaller each time compared to the optimal value function for at least one state. And the property that makes this all happen is not necessarily obvious from just this property, is the contraction property. So if you look at the max norm for v minus v prime, and then you apply the Bellman backup to v and apply it to v prime, you get two new vectors, right? the max norm here is going to be less than the max norm here, right? And we know it's strictly less than when these aren't the same because beta is less than 1. All right? So this is the contraction property. And there's a proof in the appendix, although Merger Story tells me that we need to update it a little bit, but it's not that hard of a thing to prove. You can do it basically from first principles. So this basically says that value functions get closer together if you apply the max norm, and then you can just imagine what do they get it, how, they're all sort of going towards this central point, right? It's a big balloon that's going towards the central point, which would be the optimal value function, right? So that's a contraction property. And we can use these two properties, the contraction and the fixed point, to prove that in the limit, value iteration converges to the optimal value. The proof's pretty simple. It was simple enough that we're just going to go ahead and show it here. So what we know is the following. So for any v, for any value function, v, we can write this down. V minus Bellman backup applied to v is going to be equal to b v star minus Bellman backup of v. So why is this first equality true? Fixed point property, right? We can replace v star with Bellman backup of v star because that's a fixed point. That's the first thing we did. Then we can write down this, right? This is now just writing down the contraction property. So this is going to be less than v star minus v, right? So that's kind of interesting. Already we've basically shown that if you apply the Bellman backup operator to v, you're going to get closer to v star than you were before, right? So this is, for v, this is how far away you were from v star, the optimal value. And this is how far you are after one iteration of value iteration. And so this distance is going to be less than the original distance. Make sense? All right. It's almost the end of the proof, but we'll go ahead and just finish it up. So you can apply that reasoning iteratively. Right? You can just iterate that observation and say that for any k, for any iteration, you have this property, right? So vk plus 1 is closer to v star than vk was, right? And this does not care about what value vector you started with, which is pretty interesting. So you're always going to get closer, a little bit closer in for like the maximum distance state when you apply these operators. And you can sort of inductively take this statement to mean this. So vk is going to be less than or equal to beta to the k times v star minus the initial value function, right? So this is just iteratively applying this rule here, right? And so this is looking pretty promising, right? So what's the limit of this as k goes to infinity? Well, it's going to be beta k as k goes to infinity is what? 0, right? Beta is something between 0 and 1, and it's strictly less than 1. So that's why we can write down this limit, right? So really, proving that value iteration converges to the optimal value function turns out to be a relatively simple idea. And the only thing we needed were these two properties. The fixed point property, and that's trivial to prove. It's just writing out the definition. And then the contraction property, which requires a little more mathematical manipulation to prove, but it's also not a deep thing at all. And then you just get this result. All right. So any questions about this?
This does not justify why zero initialization would be better than any other initialization.
Yeah, it doesn't. So so you can initialize to anything we can see here, right? Because the only thing that matters is beta to the k goes to 0. But if you initialize badly, like let's say if you initialize random numbers between negative a million and a million, your value function initially is going to be really far off, and it's going to take a lot of iterations to get you to where you want to be. So generally, if you can initialize to something you think might be close to the value function in the end, that's great. Yeah, but in general, this works for any initialization. All right, so any other questions? Initializing to 0 is kind of nice in the sense that you can just say the convergence time is kind of related to just sort of the size, the magnitude of the values. Because if you initialize this to 0, you just get v star here. So that's kind of nice. And that's intuitive as well. If you have larger and larger values, you kind of need to do more iterations if you're starting from 0. All right, so all set. Okay. So now, so we know it converges in the infinite limit, but your boss tells you, I want you to return a policy that's within epsilon of optimal, right? A near optimal policy. And let's say you have your value iteration algorithm. You have to decide when to stop that thing and return a policy and be able to convince your boss that it's actually within epsilon of optimal. Right? That's pretty, without ever really running the policy and testing it, we'll say. We want to do that mathematically. So that's a nice little thing to be able to do. And so we're going to talk about how to do this now. And I'm not going to go through this proof here. Again, it's not that hard. At the end of these slides, I have some appendices. And I would say I do want you to be familiar with these proofs. I want you to be able to know them. They're not deep proofs. So I'll talk more about the quizzes before them, but they are fair game for quizzes or questions around the proofs. So this is a very important property. So what this is the max norm of the difference between value functions and successive value iteration steps, right? And so basically it's saying, it says, which state changed the most from step k minus 1 to step k? Which state's value changed the most? And that's what this value is here, right? And what this property says is if that change is less than epsilon, right? So if it's small, for example, usually we'll think of epsilon as a small value, then the value function, vk, is going to be pretty close to the optimal value function, right? So it's going to be bounded by this amount here, right? So you have this extra beta. This is the thing that kills you, like 1 over 1 minus beta. That can be pretty large for a large beta, but that's the nature of how things work. If you have a really large beta, close to 1, you need to conceptually plan far in the future, right, to actually get maximum reward, because beta close to 1 means you're looking far ahead. And that conceptually means you need to have more iterations of value iteration, and you need more you need to be closer and closer to be able to not have the error accumulate over time. So makes sense. So this is nice because you can now say, this isn't exactly the question your boss asked you, but if your boss said, I want you to give me a value function that's within epsilon of the optimal value function, or let's say delta of the optimal value function in the max norm sense, you can say, okay, yeah, I could say I want this to be equal to delta, right? And I'll figure out whatever the epsilon is as my stopping condition. And I just run the algorithm until eventually the error, the difference is below epsilon. And then you can confidently say that we have this property, right? So, make sense? Now this is kind of, so this is nice, but it's not exactly the question your boss asked. Your boss cares about what is this policy going to do? How good is this policy going to be if I run it, right? And so if we remember from last time, if I just give you a value function, can you tell me what to do in a state? If I just give you a value function, no, right? So the value function just says if you're in this state, this is how good the optimal policy is, or whatever policy is being valued. It doesn't tell you what to do. So how did we say we're going to define the policy if we have a value function from value iteration?
Take all actions, choose the action with the greatest value state next.
Yeah, so somewhere in these slides we defined the notion of the greedy policy, and this is a very common thing. Let's see. Yeah, so the greedy policy. So now when we run value iteration, we're not going to put V star in there. We're going to put VK, like where the K is where we stopped. But the policy we return is going to be this greedy policy that says, okay, I'm going to look one step ahead for every action and pretend that I get VK in the next state. And whichever action looks best, that's the one I'm going to take for the policy. Right? So you need to have a model that lets you look one step ahead and the value function to define the policy. And luckily here we have those because we've been using the model to run value iteration anyway. All right? So your boss cares about, well, how good is this greedy policy? Right? That's what your boss cares about because that's what you're going to go run in the real world, whatever your environment is. Your boss isn't asking really about, your boss is not directly asking about how close this VK is to V star. Right? So does that make sense? Right? And let's try to put a finer, I guess we have a lot of that here. So this is saying a lot of things I just said. So we know how to stop and make sure our VK is close enough to the optimal value function. And if we stop, then we're going to have this greedy policy, right? This is the policy we would give our boss. And this is maybe subtle. I don't know how obvious it is. It's usually once you think about it a while, it's obvious. But the greedy policy's value is not going to be exactly equal to VK, right? I don't know if that makes sense, but so an extreme way to see this is I could give any VK, right? Any VK that I want. I could take a VK and scale it by 1,000,000 in every state, and the greedy policy is unchanged, right? So the greedy policy doesn't necessarily have anything to do with the value of the greedy policy does not necessarily have anything to do with the value you're using for your one-step look ahead, right? So just to state this again, I could take VK and I could just scale the values uniformly across the state space by 1,000,000. Right? VK is going to be much larger than it was. And will the greedy policy change? No, because everything is sort of being scaled the same way. So the greedy policy is the same, but now it's pretty clear that the VK, the scaled VK, is not the value function of the greedy policy. Okay? So we need some way of bounding the value of the greedy policy and determining when to stop value iteration so that the value of the greedy policy is close to optimal. All right? That's the thing we're actually going to run. Right? And this is where it can make your head spin a little, but it's really not that bad. But you kind of need to write down some notation for this to make sense of it. So for simplicity, we're going to define pi k of s to be the greedy policy you get when you're using VK from value iteration to define the greedy policy. Okay? So pi k, if you stop value iteration, is what you're going to return as the policy for that iteration. And we care about the value of pi k. And so we care about this value function here. Your boss wants you to guarantee that this value function is close to optimal, right? Not vk, although we're going to see that vk is ultimately what we're going to be concerned with. So intuitively, it does seem to make sense that if vk is very close to the optimal value function, it feels like, if you get close enough that v pi k should be close to optimal, right? As you get closer and closer to the optimal value function, greedy policy with respect to that should get closer and closer to an optimal policy. And the question is, how fast does that happen? Like, it could be the case that this has to get vanishingly close in order for the greedy policy to be anywhere near optimal. So we need some mathematical expressions to basically tell us this. So this is a diagram that it either confuses people or helps people. I don't know which yet. And we'll talk about it. This is just trying to show you how we're going to get this bound. And this is just showing you the process. So we get our MDP and beta as input, right? That's what I give you. It's policy optimization. Here's your MDP, here's beta, give me the optimal policy. And then from that, we run value iteration for a while. We get VK out. That's what we get as the output. And then with the transition model, we can define the greedy policy pi k, right? And we're interested in whatever the policy evaluation of pi k is, right? So we want to bound this. And so one thing we can do is there's a result in this. I think this is in the appendix. I've got to check. I think we put it in the appendix. So this is kind of an analog theorem, you could say. So if Vk minus V star is less than lambda, okay? So if Vk is pretty close to V star, and we already know how to stop the algorithm to achieve that, right? We've already said that once successive iterations are small changes, we can bound how close Vk is to this. So if this value function is close to optimal, or it's within lambda, then this is a theorem that the greedy policy in terms of Vk is also close to optimal with these extra things, right? So your lambda close here, your lambda, with these extra things here, right? So this again has that 1 over 1 minus beta, and that's sort of the thing that makes this kind of explode. But you can always pick a small enough value of lambda, right, so that this will be arbitrarily small. So your boss says, I want you to be within 0.1 of optimal, your greedy policy. You say, okay, yeah, so I can just say I'm going to pick a lambda such that this expression is less than 0.1. All right? So once we figured out what the lambda is that we need, then we just need to run value iteration long enough so that Vk is within distance lambda. And that's where we use the result that we just had, right? So we know that if this is less than epsilon, the successive runs are less than epsilon, then Vk is going to be less than or equal to this. And so these two results, you can sort of back chain to figure out how to stop value iteration so that you achieve this final result. And we'll just go through that here. So this is the property that we just talked about. And now we can just run this until we can bound lambda. And I think this is just showing you, you could fill in the text here, but it's really just a bunch of inequalities. All right. So our goal is to bound this less than delta. It gets confusing because you have to have a few different bounds. You have lambda, epsilon, and delta. Delta is what your boss cares about. Okay, that's the 0.1. And then we would apply this thing here. We know that to achieve this, we want this thing to be less than delta, right? And we could compute what value of lambda you need for that to happen. And then we say, okay, to achieve that lambda, we want this to be less than whatever lambda was, and then we can compute the epsilon. And if you go through all of that, then you can derive this result. This is the bottom line after a little bit of algebra. So if the successive iterations, the max norm are less than this value here, then the algorithm will actually do this. It will have this guarantee. All right? So is that clear? All right? And it's kind of interesting. So I always like to check these things qualitatively, right? When you see a bound like this, because it's so easy to mix up your numerators and denominators. But why does this make sense, right? At first, when I was just looking at this right now, I'm like, is this right or did I screw up? But when beta is really large, close to 1, this gets close to 0, right? Now, why does that make sense in this context? So when beta is large, is it an easier or a harder planning problem, do you think? It's going to be harder, right? And would we expect value iteration to have to run longer? Right? Right. And so when beta is large, this is going to be smaller. And you're going to have to run value iteration a longer time to achieve like successive iterations being smaller change than this quantity here. So it does make sense that this 1 minus beta is in the numerator as opposed to the denominator, right? If you have a very small beta close to 0, then this is going to be a very fast converging process. Although you do get this in the denominator. Not sure how those. Yeah, so not sure how the analysis goes there, but yeah, that part doesn't make as intuitive sense to me. Not sure if that would be tight bound or not, but nonetheless, you can derive this very easily from these two facts. So any questions about this? Sometimes this confuses people, but I will, on your homework, I'll say run value iteration so that you guarantee the optimal policy is within blah of optimal, right? And you'll have to be able to do this. All right. So now this is going to be relevant to your homework on value iteration. So what we just talked about was something called synchronous value iteration, because every iteration you do a Bellman backup at every state using VK to get VK plus 1, right? It turns out that you don't have to do this synchronously to get convergence. And the same type of analysis works. You can basically have an algorithm that takes a random state, picks a random state, does a Bellman backup, then picks another random state, does a Bellman backup. As long as you're guaranteed that however you're picking those states will pick every state infinitely often in the infinite limit, we're guaranteed that the asynchronous version will converge, right? So the asynchronous version is you do each state, you'll just update the value function for one state. You'll get a new VK, then you'll update it for another state, you'll get a new VK, as opposed to updating them all each time you get a new VK. And yeah, so this is kind of interesting. So if you're doing an asynchronous version, do you need to store 2 copies of this? No. Right? You just you almost do the updates in place. So you have a memory allocation for the value function, and you just do a backup at a state and immediately change the value. Right? So you don't need to have 2 copies of the array. There may be some reasons to do that, but you don't have to conceptually. Right? Previously we did because we had to update all the states based on VK before we could get VK plus 1. All right? So that's kind of cool. And actually that asynchronous variant, that's we're going to see later on, that brings us basically to Q-learning. You'll add one more approximation on top of this to get the Q-learning algorithm. For those of you who might be familiar, you'll add on a stochastic approximation. But ultimately, it's about this convergence of the asynchronous variant. Right. So any questions about that? Yes?
Does this work only because the Bellman-Packet equation is a convex equation?
It's a contraction operator. Yeah. So the contraction property is basically central to all of these things. Yeah. Any other questions?
Does the Q-learning being an optimistic estimation has anything to do with V pi k not being equal to VK?
V pi k. So you're talking about Q-learning optimistic initialization? Or?
Q-learning being an optimistic estimation of the actual Q.
Well, Q-learning may or may not be optimistic of the. Yeah, you may end up maybe pessimistic sometimes. There's no general properties that it will maintain like an optimistic variant. Although you could make a version of Q-learning that does. Like if you're doing optimistic initialization, it might always maintain an upper bound.
There's no perfect correlation between these two.
Yeah, Q-learning is a little bit, so once you get to Q-learning, you have this whole stochastic approximation aspect to it. And so it can do wacky things in between. Like here we're doing real expectations. We're able to compute the expected value over all future states, the exact future value. Q-learning can only like sample one of them and do an update. It's like stochastic gradient descent versus gradient descent. We'll get to that in more detail when we get to Q-learning. Any other questions? Okay. So, the last few minutes, I wanted to go back to policy evaluation and revisit that because so how did we've already done policy evaluation. How did we do that? Like, what was the machinery to do policy evaluation? Does anybody remember? Was it an iterative process, or did we apply something? Remember there were these equations, n equations, and n unknowns? So what did we have to do computationally to do policy evaluation? Yeah, we just had to solve a linear system. So we had to do a matrix inverse or whatever you want to do to solve the linear system. That can be a little bit annoying if you have millions of states. You're going to have to start getting into like dealing with sparse matrices and things, and so it would be really nice if we could have a more iterative process for doing policy evaluation. And it turns out that once you have the fact that value iteration converges, you can very easily come up with an iterative policy evaluation process. And it's actually a very simple idea. So if I give you a policy in an MDP, we're going to create a new MDP. It's going to be a trivial MDP that's identical to the MDP, except you remove all actions that are not taken by the policy. Okay? So it's an MDP, and so let's look at this. So here's your original MDP here. It has, 2 actions in every state, right? What we're going to do is we're going to say that M pi, this is a new MDP that sort of removes all actions. There's only one action in every state now, which is kind of a trivial MDP, right? But that's okay. It's still an MDP. Value iteration will still converge for this MDP. Now, what's the optimal policy for this new MDP? Or pi, right? How many policies are there for this MDP? There's just one, right? There's only one action in every state for this new MDP. That's the action that pi selected. And so there's just one policy, and so that's the optimal policy. And we just said that value iteration computes the value function of the optimal policy. So if you run value iteration on this MDP, it's going to converge to the value of pi, right? And that's pretty much it. And so we'll review this next time, but that's the basis for how you can get an iterative algorithm for policy evaluation. All right. So I think your homework's due Monday, right? End of Monday, is that what I said? Yeah. So it's on Canvas. So be working on that, and then we should have the next homework ready to go by the time you turn this one in. All right. So I'll see you on Monday.